And today he's going to speak about the study of the polar caps on Mars and what they can tell us about the past climate there. So I'll hand off.
Thanks. Okay. Can you hear me? The light's green. Oh, okay. Oh. Does this work? Okay, much better, thank you. Okay, so, thanks for the invitation. Hope I can sort of tell you not just about Mars, but sort of set Mars in a little bit of perspective in the solar system. So, the first thing that you might wonder about is, here we sit in a neighborhood in this solar system. There are 3 rocky planets that are not all that much different in their distance from the sun, and they are wildly different in terms of their entire environments. You have Venus here, which this is not a visible light image because it wouldn't show any features. This is I think an IR image. But so Venus with its clouds, Earth, and Mars. And these places are really completely different. Venus is about 72% of the distance of the Earth to the Sun. That is, it orbits the Sun at 72% close, about 72% of the distance that the Earth does. It's almost the same radius. Surface gravity on Venus is about 9/10 that of Earth, and yet the surface temperature is hot enough to melt lead. Not only that, the surface atmospheric pressure is enough to be pretty crushing, and liquid water, or any water, vapor or anything, is in pretty sparse supply. So it's very dry, it's crushingly heavy in the atmosphere, and it's hot as blazes. This is a colored version of a radar, a DEM derived from radar imagery of a volcano on the surface of Venus. Earth, we know and love. It's sort of by definition, its mean orbital radius is 1 astronomical unit. Equatorial radius, 6,400 kilometers. You might not know that the mean surface temperature of the Earth is about 15 C. And mean pressure actually turned out to be defined more or less this way, 1 bar. And we've got water all over the place, a lot of water. Mars, 1.5 astronomical units away from the Sun. So about half again as far from the Sun as the Earth is. It's a little over half the Earth's radius. Surface gravity is about 38% of the Earth's gravity. The mean surface temperature is pretty chilly. That's something like the coldest temperature recorded on the surface of the Earth at Vostok Station in East Antarctica. But that's what it is averaged over the whole planet all the time. Not only that, there's hardly any air, 0.6% of what there is on the Earth. Most of the air there is carbon dioxide, some nitrogen. You can't breathe it. And Mars is a cold, very dry desert. It makes, for instance, the dry valleys of Antarctica, which are our sort of favorite cold, dry desert, look pretty wet by comparison, by a factor of 50 or so, if I recall right. So Mars is incredibly dry. Seems like very thin air, enough to raise winds, but still very thin, very cold. How in the world did this happen? Planetary science has had as one of its main questions for a while now, how can 3 planets, not that different in density, made out of more or less the same stuff, in the same neighborhood in a solar system, how can they turn out so different? Even if you were reading science fiction from the mid-20th century, Venus was supposed to have jungles and steaming sort of Cretaceous era plants, and it was supposed to be a pretty interesting place to go visit, not this place that you couldn't survive for an instant. Mars was imagined to be a place a lot like Earth, partly on the basis of people's observations through telescopes that turned out to extrapolate much more than they should have. But Edgar Rice Burroughs wrote about Barsoom with fabulous kingdoms of people, and even more recently, Ray Bradbury wrote the Martian Chronicles. That kind of, in the words of this author, it was sort of like Taos without the tourists. You had sort of tender, slender, tanned people, gentle-spirited. By the way, there's an article in the New Yorker that's just out this week about the recent history of the exploration of Mars that I recommend very highly if you have a little time. That's where that phrase came from. All right, so, well, I don't have time to, and I'm actually not expert about how Venus came to be the way it is. But I can talk a little bit about Mars. The short answer for Mars, at least according to what we think as of the last 7 or 8 years, subject to some revision, but probably not a wholesale revision, is the sphere. And there is a pretty strong isotopic signature in the water that's left on Mars now to indicate that the sun blew away most of the water with the atmosphere. That is a large part of the original water inventory of Mars. So Mars basically just it started out too small, it got picked on, and got beaten up. And all of this happened a long time ago. I mean, this story was well along and maybe mostly complete by 3.5 billion years ago. The record of cyanobacteria on Earth, the main, what we think is the main start of oxygenic photosynthesis on Earth, goes to 2.7 billion years ago. So all this stuff was happening pretty early on relative to everything that happened with regard to life on Earth. These are the volcanoes in the equatorial region of Mars. This is Olympus Mons, the largest volcano in the solar system. Much taller than Everest. Something like 25 kilometers tall. It's an astounding volcano. And we find geologic evidence of glaciers that have been on the flanks of this set of volcanoes, relatively vertically exaggerated. So you can see it's a lump of ice that on the one hand looks kind of familiar to a terrestrial glaciologist, and on the other hand is pretty unworldly. For context, every year, these are images from the Hubble telescope, but every year there's a great big CO2 snow and frost cap that forms in the winter hemisphere of Mars. So it's dry ice, carbon dioxide ice, and then it retreats and it leaves this remnant which lasts through the summer, and that's water ice. And that repeats year after year. So there's this great big seasonal cap, but we're going to talk just about this residual cap, the one that lasts through longer times. It's the largest reservoir of water ice that we can see, the one we know about for sure, in contact with the atmosphere seasonally. It's thought to have a climate record, but it has a relevance especially to people who want to know whether, if life ever developed on Mars, is there a ghost of a chance that it survives to the present day? And according to modeling and data from the Mars Phoenix lander, one of the really key things in understanding whether there's enough water for organisms that we understand to metabolize on Mars is the question of whether that North Polar cap survives over millions of years or not. If it survives over millions of years, there's enough humidity in enough sort of low spots on Mars that bugs that we know about from Earth might just eke out a living. And if it doesn't survive, it gets too dry everywhere. And even the hardiest bugs that we know about from Earth would have died out. So this question of the fate of the North Polar cap is relevant to planetary science, but it's relevant to what we call astrobiology, the study of life in the universe. So, things we'd like to find out is, does that cap go away entirely every few million years, or does it somehow survive? How do we read the climate record in there? And what's it doing right now? So to start to get at those questions, my colleagues and I, several years ago, began by noticing something that's kind of peculiarly similar to a big ice cap on Earth. This is the Antarctic ice cap. And what I'm showing you is a digital elevation model that has been colored in grayscales so that places that are high are bright white and places that are flat are bright white. So places that are high and flat are the brightest. And you see these spines that go through here like this. Those are drainage divides, just like drainage divides in the Cascades. Ice on this side flows down this way. Ice on this side flows down that way. You also, just in passing, you notice this big flat bright area there. That's Lake Vostok. There is, under the Antarctic ice sheet, 4 kilometers below the surface, so under 4 kilometers of ice, there is a lake the size of Lake Ontario, something like 800 meters deep. It turns out it's one of about 300 lakes beneath the Antarctic ice cap. They are almost entirely unexplored. Anyway, that's another project of mine. I'll tell you about it a different time. But so my colleague Jonathan Bamber was here several years ago on sabbatical, and he had made this shaded digital elevation model precisely because he wanted to highlight these drainage divides and see where they are. So we decided to try that on Mars. This was the usual way of shading a digital elevation model on Mars. We did it Jonathan's way, and what we noticed right away is that there's this chewed up but bright ridge coming down on this lobe of ice that looks relatively new. We wondered if that might be an ice divide. That would be a key feature that we use to decipher how an ice sheet on Earth is working. Just because it looks like that doesn't mean it is that, but it gave us something to test. And what we wanted to test is, well, do ice caps on Mars flow the way the Antarctic ice cap on Earth flows, for example? Well, on the one hand, it has to. Ice is a ductile material. There's a lump of it. It's sitting in gravity. Gravity's pulling it down. It has to flow, but the real question is, does it flow fast enough to have an effect on the ice cap, or do other things that happen to the ice cap happen so fast that they completely dominate how the ice cap looks? And the way you get at that is you can sort of define this ratio of times. The time it takes for surface mass to come and go, for the atmosphere to put mass on or take it off from the ice sheet, divided by the time it takes for ice to move through the ice sheet from a place where it's deposited to a place where it leaves the ice sheet. And on Earth, this ratio is always somewhere around 1. And we would like to find out what's the evidence for what it may be on Mars. So the way we got around that, or we started to get to that, first actually we looked at the topography of this part of the Martian North Polar layered deposits, as they're called. Initially, before we knew it was ice, people wanted to be quite cautious about what they called this thing. We now know it's ice. But it has these troughs in it, and we didn't quite know what to do with that topography. No ice on Earth has troughs on it like that. We tried a few different things, and finally we decided to just look at the surface between the troughs. And when we did that, this is what happens if you cut out the troughs, and then you sort of interpolate across the tops of them, and you reconstruct what the ice might have been like before there were troughs there. And then you look at what would the paths of ice flowing in an ice mass like that be. And so there are 40 red and white paths here, and then there are a few blue ones. The red and white ones, turns out, have a shape that tells us that there was ice flowing on Mars rather recently. There was dynamic ice in that sense in the fairly recent past, and I'm going to show you how we know that. We know that by using what physicists are fond of calling a spherical cow model. And if you were graduate students, I'd really stress to you that you want to always do some sophisticated thing. You want to show your professors and your colleagues how smart you are, so you want to leap to doing something really complicated and sophisticated. it's often a mistake. Often it makes much more sense to start out with the simplest model that you can think of that might have the right physics in it and see what it tells you, because if it's right, you learn something, and if it's wrong, you learn something from how it's wrong that tells you what additional physics to put in. So, we started out with a spherical cow. Spherical cow, in this case, is a really simple model for how an ice sheet flows. It neglects all kinds of stuff, but maybe it captures just enough of the right stuff. That was the hope. Actually, to tell you the truth, I didn't think the model would work at all, but I thought the way it failed would be informative. And for those of you that are more technically minded, it turns out that this model gives you a prediction for the surface shape, the topographic shape of the ice. And the way that works is you have an ice mass, and you're putting mass on up here, usually at high elevations, and then mass leaves the ice sheet at lower elevations, and there has to be ice flow to equilibrate those things. And, so when this happens, it turns out that the physics of how the ice flows sets the slope of this surface in a way that's really diagnostic. The shape of an ice mass tells you if that physics is operating or not. And so when we looked in places, for instance, where those blue lines are, places that look very chewed up and ablated, and they don't look like, we would expect a flowing ice mass to look, the surface topography doesn't look like the surface topography of a flowing ice mass. What I'm showing you here are topographic data in the black. This is for elevation along one of those blue lines, in this case, that I was showing you. Notice that there's about 100 to 1 or so vertical exaggeration. And the heavy black line is where the places we would pick out as being between the troughs. But even between the troughs, the red and the green lines are attempts to fit a flow model to this topography, and it's not very good. It doesn't look like a flowing ice mass. But if you go over to those red and white lines, those lines cover an area that's about 400 kilometers on a side on the Martian North Polar Cap. And those places between the troughs fit very well with the topography that you would expect if the ice had been moving, like a terrestrial ice mass. This is a little bit of comparative glaciology, taking something you learn on the Earth, using it on Mars to find out something new. So we got a result like this in one place, and we were encouraged, so we started to look somewhere else. We saw it over and over and over, everywhere on those red and white lines. And not only that some things that we inferred about where mass was accumulating and where mass was getting cooked off on the ice sheet, those things also told a consistent story. So this is a story told to you by the topography of an ice mass that is consistent from place to place, and it seems to say, wow, not only has Mars got ice moving around the planet from the equator to the poles and back again, but near the poles, at least in this place, reasonably recently, so the evidence is preserved, we see behavior that's recognizable from Earth. It's the behavior of a flowing ice mass. So this tells us that we can begin to apply things that we know from Earth about reading the layer record in a flowing ice mass, in principle, to Mars. And it says that Mars it really is true to what Vic Baker said. For all of its being old and cold, it is still dynamic to the present day. So this is that part about that the shape is generic. And so what I've done here is to take surface profiles of ice masses from Earth and Mars, and I've normalized them. That is, I've divided, for instance, the profile by its length, and I've divided it by the height at its highest point so I can compare them. And this is East Antarctica, along the Vostok-Mirny Traverse, actually. And this is a model fit like the one that I was just using to those data. So you can see that East Antarctica has the shape of a flowing ice mass. It's flowing, up high a few tens of meters a year, near the coast maybe a few hundreds of meters per year. This is a place in Canada where there's an ice cap that is being, it's melting and it's evaporating into the atmosphere too fast for the ice flow to keep up. So it's a place that is shaped by something other than ice flow. It's shaped by exchange with the atmosphere. It's called the Mayan ice cap, and it doesn't look anything like East Antarctica, and neither does it look anything like that part of Mars that I was just showing you. This is one of the same plots that I just showed you for comparison. You can see Mars actually looks a lot more like East Antarctica in that particular place than it looks like this place on Earth that's not flowing ice. So the conclusion is that we found a kind of surprisingly terrestrial-like process operating on Mars in the fairly recent past. And so we interpret that in terms of those troughs. Remember, I was only looking between the troughs. This topography between the troughs is what would be there if there had been ice in the places where there's thin Martian air in the troughs now. So we think that what has happened is that we started out, there was a flowing ice sheet sometime in the past, and then the flow must have stopped, and that's when the troughs cut in. This is just a section of topography across that part of the Martian North Polar Cap. And that what survives today is that relic surface, and that's what's informing us about what happened in the past. That picture makes a further prediction that you can test. In particular, it says that in the places in the past, when this thing was flowing, where the ice was getting cooked off the surface, you ought to see layers inside the ice coming up toward the surface. And you shouldn't see that in places where the ice was getting piled on by the atmosphere. And if either of those two, well, especially if this part about the layers not hitting the surface up high goes wrong, you're just wrong with your scenario. We did check that, and they don't bump into the ice up high, but when you look down low, there are some places where we can test that. So what I'm showing you here are tracks from a radar that is in orbit around Mars on the Mars Reconnaissance Orbiter. It's a sounding radar. So it has a wavelength in free space that's like from me to the door there, a little more than 10 meters, but not much more. And it transmits a signal down to the surface, and it listens for echoes not only from the surface but from the subsurface. So we can look inside things that are relatively transparent to radar waves. Ice, fortuitously, is one of those things. So along these tracks, these are satellite tracks, the black lines. Along these tracks, we can look into the ice and see that there are, in fact, layers inside this Martian ice. Not too surprising, because we saw them cropping out in the places where there are cuts into the ice, but still, it's nice to trace them. And then we can look along the paths that the ice flow would have taken according to our model, or our scenario. And those are the white lines. And so there are a few places here where you get topography right down near the end of the flow lines that probably was there at the time that the ice was flowing. So we have a few places where this is a model fit to the topography. Again, the heavy black line is what we call intertrough topography. And there's a little bit preserved down here that fits pretty well with what we thought the surface should be in that scenario. So we think that's surviving relic topography. And the question is, well, okay, are there layers starting to come up toward the surface there or not? Well, this is a radar picture, and I'm sorry it's a little blurry. Keep in mind it was It was taken from 300 kilometers up with a radar that radiates about 10 watts. It's like your CB radio. It's amazing that you can hear the echo back at all. In any case, you have sort of some layers here. I hope you can trace them. They're sort of parallel to the surface, and then they start to come up and intersect the surface there. So it seems like our scenario, after we proposed it, survived this later test. So we think that that's right, that there was this place on Mars that was acting sort of like a terrestrial glacier. Mars is active in the recent past, but as our colleagues in the planetary science community were quick to point out, this does create a conundrum. Remember I told you that the average surface temperature of the Martian North Polar Cap is about minus 111 C. It's a lot colder than Earth. Not only that, I told you that Mars was small and it cooled off early in its history, so the heat coming up through the ground on Mars is almost surely substantially less than the heat that comes up through the ground on Earth. You know, we have geothermal heat. People try to make power plants from that. It's what you see vividly in a volcano. We have much less of that on Mars. So you have cold temperatures on the surface of ice on Mars. You have not such warm temperatures down deep in the ground on Mars. Means that all the ice in that North Polar Cap must be pretty cold. And that means that, well, it turns out that ice is a pretty good rock at these cold temperatures, at like minus 100 C. You know, we're used to seeing ice pretty close to its melting temperature. And, you know, then it's pretty ductile. We see glaciers that flow. When you see rock at pretty close to its melting temperature, we call it lava. When rock is far from its melting temperature, it's really hard. And ice is the same way. When it's way below its melting temperature, it's very hard. It doesn't flow or deform very quickly. In fact, actually in the outer solar system, ice is sort of the typical country rock in a lot of places. Yeah, it's even colder out there. But on Mars, it's cold enough that if you ask, how fast should ice flow? We think we understand something about the physics of how ice moves under this deforming effect of gravity, pulling it down. And you look at what's the topography that we observe, and what should the topography be if the ice could flow as fast as it flows at these cold temperatures with, you know, the little bit of mass that's being piled on it today in the Martian climate? And the answer is, well, it would have to be really steep to get enough, what we say, driving stress, enough stress from gravity pulling it down to make it go. That's not what we observe. So seeing this shape that's characteristic of ice at a much warmer temperature raises the big question. So if ice was flowing recently on Mars, how did it get warm enough to flow? This is just to put some numbers to that. In the present climate of Mars, this is from other measurements, how much mass we think is getting pulled off the Martian ice cap each year. The response time, the time to get the ice mass to equilibrate into that shape that I showed you, is more than 10 times the age of the universe. So that didn't happen. You can then play with the numbers and see what it would take to get something that might be geologically possible. That requires a pretty high temperature if the ice is pure. So now I come to the point of sort of where we are in this investigation now, and I'll say just a little bit about where we're headed. It's hard to imagine that it ever got that warm at the base of the Martian ice, but you might have heard that the Phoenix lander near the North Pole of Mars, actually about 67 degrees north, I think, found this chemical in the soil, perchlorate. You know, we know perchlorates on Earth because they're associated with making rocket fuel. They're usually a groundwater pollutant near places that manufacture rocket fuel. But it occurs naturally on Mars. It occurs a little bit naturally on Earth too, but more of it occurs naturally on Mars. And it's in the soil, and it has this peculiar property that if you mix perchlorate and water, you can make mixtures, if you have, say, magnesium perchlorate, you can make mixtures that don't freeze until about minus 70 C. So you can, I mean, that's a really cold brine. And there is evidence now also from the Curiosity lander on Mars that there are perchlorates all over the planet on Mars. Turns out that if you mix some of this chemical into ice or into water and then you freeze it to make ice, that ice is soft, at much softer than regular water ice, pure water ice, at much lower temperatures than pure ice. And so we are pursuing now, we and some colleagues at MIT who put ice in presses and measure how soft it is, the idea that this chemical that we find on Mars might be why ice is a lot more mobile on Mars than it is on Earth. It's squishier and flows around. And so that brings you, oh yes, so that brings you pretty much up to the present state of where we are in the research. We have this evidence that there's not much heat flow on Mars because this lump of ice isn't pressing the surface down, the crust of Mars down. That means it's cold. Can't warm the temperature up enough. We don't know how it got warm enough to make pure ice flow, but we think we're closing in on how ice could flow if it wasn't pure. And so the upshot of that is that Mars is old and cold. It's not clear whether anything ever lived there. It would have had to have gotten started pretty quickly, it seems like. But if anything did live there, it would be really interesting to know if anything survives. And pertinent to that question is how ice moves around the planet now. Does ice move around so that some places stay humid enough for some bugs, some cold-loving microbes, to wake up periodically, repair their DNA or whatever it is they have, the way we do see in the Antarctic dry valleys, and might they live even to the present day? That's a big open question, but it is directly related to this question of how ice moves around on Mars. The North Polar Cap being a key reservoir and also a record keeper does seem to flow. We're working on whether we can, in fact, show that it moves fast enough to make this whole story hang together. And overall, we have this picture of polar caps on Mars as sort of these funny, sort of sloppy layer cakes. That place that I showed you seems to have just been the most recent place where the atmosphere dumped a lot of water ice on the surface, probably as the rotational axis of Mars was rocking back and forth. And that seems to go on and on over time. It suggests a way that you might have some ongoing story on Mars, certainly geologically, maybe even biologically. So that's the story to this point. Sure. Sure. The question is, why is there so much perchlorate on Mars? Our local expert on that is actually David Catling in this department. But the short version, as I understand it, is that you have high energy light from the sun, ultraviolet light, bombarding the atmosphere of Mars, and you have chlorine left around on the surface of Mars from the time of its formation. And you have oxygen-containing compounds. Not free oxygen, but oxygen locked up in rocks. And this high-energy light photolyzes, that is, breaks the chemical bonds in the rocks and the chlorine-containing compounds. And when these compounds recombine, some of them form this perchlorate, which is chlorine and 4 oxygen atoms. And so over time, that stuff builds up because Mars is a pretty dry place. On Earth, we have this process, and we observe it only in really the very driest places on Earth, the Antarctic dry valleys and a place in Chile called the Atacama Desert. Doesn't build up as much there because even the Atacama Desert is wetter than Mars. But on Mars, apparently the stuff can build up over geologic time. Yes?
With the loss of ice due to the ablation, does that sublimate and go into the little atmosphere with the water ice?
Yes.
And is that stripped away?
Well, so some of it is probably lost each year. So what we observe, actually we've observed since Viking, is that when that seasonal CO2 frost all evaporates away in the summer in the north, then we get a pulse of water vapor up in the atmosphere. We can see it spectroscopically. So some of that water vapor from the North Polar Cap is released up into the atmosphere, and some of that must be photolized also by the sun and stripped away by the solar wind every year. So, but most of it goes and gets deposited somewhere or circulates around in the atmosphere until it gets cold again, and then it gets redeposited in the north. But you are losing a little bit every year over a long time.
It only deposits in the north?
No, there is also a southern cap, and it's a more bizarre place. It has a dry ice veneer, just a thin covering, maybe 10 meters or so thick, all year long. There are some places where the water ice patches break through. But it's higher, it's on higher elevation terrain, and it's colder. And it's even more bizarre and otherworldly. So it doesn't, but at the present moment, it doesn't seem to participate so much in that annual water cycle. Yeah.
About is even with perchlorate melting out the ice, making it flow faster, did the ice still need to sometimes be a little bit warmer in the past so that it can use as long as in the past conditions for life better?
Well, okay, so a couple parts to that question. The question is, even with the perchlorate in the environment, wouldn't the ice still have to be somewhat warmer in order to flow? And would that be warm enough to be relevant to the question of life recently? So let me break that down. Yeah, it turns out that even with perchlorate in the ice, making it soft, the thing that is interesting about perchlorate is it makes the ice soft at quite low temperatures, like minus 70 Celsius. And those are temperatures that we think the base of the North Polar Cap might have reached. So that could explain why the ice could move fast enough to put itself into this shape that we observe. Now, that's separate, though, from the question of, would you have any liquid water, or would it be wet enough someplace else on the planet? Not necessarily in the polar regions. But yeah, these perchlorates and other salts might be able to lower the melting point of water so that you have little bits of brine in lots of places around Mars at lower latitudes, frequently enough for something biological to happen. It's quite a large open question. It's not easy to discuss because, salts are hard for living organisms to use. Maybe some bugs are adapted in ways that we haven't seen yet. A lot of open questions.